Bismillahirrahmanirrahim. Today we derive FEM equations for static stress analysis problems. We'll be employing the principle of minimum potential energy. You are already familiar with that from our previous lectures. The minimum potential energy principle states that the potential energy for any system at equilibrium is minimum. So any system minimizes its potential energy at its equilibrium position. So this is the expression for potential energy. This is the strain energy. This is the work potential. Let's take one by one both these terms and see what we get. Now, starting with the strain energy, in any solid, let's take a differential volume dV, and for this differential volume, the strain energy d lambda will be now we know that strain energy is the product of stress and strain. This is a dot product, so you have this transpose here, so that relevant components of strain multiply with relevant components of stress, and this transpose only does that function. Now, what is this part? If there is any thermal strains involved, then you have to take those out from the expression, because thermal strains, they don't play a part in strain energies. Strain energy is basically any forces that cause stresses in a body and corresponding strains, and you have the product of stress and strain, and this 1 by 2, this only tells you that we are assuming that the load or the stress applied is gradual, not abrupt. So if there is any thermal strain component involved, it plays no part in strain energy, so you have to subtract that part from the total strain energy. This is total strain vector. This one is initial or thermal strain vector. So we subtract this part, the initial strain part, from the total to get the mechanical strain. Then mechanical strain is what plays a part in strain energy. Now, if this is a differential for a differential volume, this is the expression. What if it's a finite volume? We are dealing with finite elements, so the volume will have some finite volume. This element will have some finite volume. What about this? Obviously, for this element E, volume with an volume of element E, the whole strain energy for this whole volume E will be equal to now you have to integrate it over the whole volume simply. Now we have two variables, epsilon, sigma, but we also know that there is a relationship that relates these two. We know that sigma equal to d. This is the constitutive equation, also called Hooke's law. So we can get rid of one of these variables to get one variable, because both are interrelated. But one thing before we do that, just like we subtracted the initial or thermal strains from the total strain to get mechanical strains, here also the relationship between stresses and strains, that is the Hooke's law, that is between stresses and the mechanical strains, not total strains, because thermal strains have nothing to do directly with the stresses. So you have to, again, if there are any components of thermal strain, we have to we have to differentiate between the two and subtract it from the total strain to get mechanical strain, and that mechanical strain is obviously linked with the mechanical stress, the stress via matrix D. Now this D obviously will take different forms, we'll see as we proceed. Now if we put in the value, we just replace this sigma, then we can get rid of the sigma altogether. Just putting in the values, replacing this sigma and this sigma by this expression. Obviously the volume integral will stay. Now if we simplify, it's very obvious that it's quite an ominous looking expression, but you do realize that all these when you multiply them, they'll just give you a number. It's a scalar. We're talking about an energy here. So this multiplied by this, these are just dot products, 3 components or 6 components here, 3 or 6 components here, or in 1D case maybe 1 component each. You multiply them and you just get a number. So here too you'll get a number. So if thought in that way, then this and this are the same things. It doesn't matter, you have on the left hand side you have epsilon naught, or here you have epsilon, and on the right hand side here you have epsilon. So it doesn't matter, it's the same thing. We can combine them together. This will become 1. You get, this is the expression. Now recall from your previous lectures that we can write epsilon vector in terms of a matrix called B matrix, which links the nodal displacement values to the epsilon values. So if we employ this, because ultimately we are talking about, we are dealing with FEM, and FEM we deal with the nodal displacements, not the general expressions of displacement. So these nodal displacements, we have to convert everything into this form. So we can use, instead of this epsilon, we can use this expression. And if it's an epsilon transpose like here, then obviously this expression, considering the multipliability, this becomes opposite in sequence, U transpose and B transpose. So putting these values here, U transpose B transpose D as it is. Now this, in this case, is simply B U minus similarly U transpose B transpose D epsilon. We don't have an expression of epsilon naught, it is as it is, plus again there's no change here. So this is your expression for lambda strain energy. Now we have to deal with the next quantity of interest, that is the work potential. Now here we'll be dealing with stress analysis problems with considering all sorts of loadings. When you did the minimum potential energy last time, we just took a very simple element and a very simple loading. But here we have to deal with all sorts of loading. Now, what are the different types of loadings in stress analysis problem? For example, if again taking this as a body, and let's say there is the element, in this case the element is here, the element we are talking about is here. Now, what sorts of forces can it be subjected to? Obviously, the simplest one is at any node there will be a certain load P. This is a very simple load. We have dealt with this. There is no difficulty here. But there are two additional types of loadings, and those loadings let's discuss. First of all, there could be the weight of the structure involved, and if the weight of the structure is involved, then if this is the x-axis and this is the y-axis, then if it's weight, then it will be directly downwards. But this downward pull for this whole body and also for this element will be if I draw the element here and there's some, obviously it has some dimensions, then the whole body of this element is subject to this load, not just any surface or any one point, but the whole body. So this in this case it will be just the y direction load. But generally speaking, there could be magnetism, there could be any kind of body force, and it could have an arbitrary direction like this. In this case, let's call it a vector with this sort of loading, and the loading here will be in Newton per cubic millimeters, because when you multiply this with the cubic millimeter of this volume, you'll get newtons. Here the load is obviously in newtons, so loading has to be always has to have the same units. So this sort of body forces will always have units of Newton per cubic millimeter, because they apply on the whole body as compared to one point or one surface. Now, what is the other kind of loading? It could be that for an element which is on the surface, let's again write it like this. This is the element and happens to be on the surface, then this surface only can be subject to some sort of, again, surface loading. And this surface loading, distributed surface loading, not like a concentrated load on one point, but on the whole surface. So now this could be again in an arbitrary direction. So we say that that vector is this. It could be, for example, it could be in an arbitrary direction like this with components in x, y, and z direction. But again, this is not at one point of the whole body. So of necessity, these quantities must be then in Newton per square millimeter, because when you multiply this by this surface only, this surface area only, you get the total amount of force. So on the right hand side vector, we expect the force vector to come. It will be a combination of all these forces, and all these must have the same unit, so these quantities must hold. So let's deal with all these types of loadings one by one. First of all, let's go. So we are again, so that we don't lose track, we are talking about the work potential here. Work potential as achieved by the three types of loadings: concentrated load, concentrated loads, body forces, let's call them surface distributed forces. This would be also be a surface load. Obviously it has to be on the surface. This also is on the surface. This need not be on the surface. It can be this element, or it can be an element inside, because this applies to the body. So let's see one by one what we can make of these expressions for the work potential. So first of all, body forces. Now, if work potential done by the body forces, if it was not an element with volume dV, but an element with a volume V as it was just a differential element dV, what would have been the contribution of body forces for work potential? It would have been simply UVW. These are the three displacement components. At one point, one point can only have one U, one V, and one W, and the body forces applied are, so you would have simply multiply this one displacement component with one force component, displacement force, you to have work done, work potential. But now obviously this is not the case. This body force doesn't act on one point, obviously. That's why this has units of Newton per cubic meter. It acts on a volume, not one point. So what all you have to do is you have to integrate this expression over the whole volume of the element. This this is the expression for one point. This one is the expression for one point, but you have to integrate this over the whole volume. So if I write it in symbolic form, this is general displacement vector, and this is x, y, z, and you have this expression. Now also recall from your previous lectures that we have a very convenient expression for the general displacement vector, and this is the n matrix which links the nodal displacement. This is capital U, this is small u. So capital U means the nodal displacement. We need everything in nodal displacement. This is FEM. We are converting everything from general expressions to the nodal values. So if I put the values here, so similarly this U T will obviously become U transpose N transpose, and this becomes simply U transpose N transpose X Y Z. This is the expression for work potential or originating in body forces. Now similarly for surface distributed forces, we follow the same thinking. Here we'll just let's P, because these are like pressure, so for want of a good word, let's denote it like WP. Now similarly, if it was just on one point, it's not one point, so the whole surface. But if it was for differential element with point, then sorry, here we have Px, Py, Pz. Just have displacement for one point, obviously one load in one direction, displacement in that direction, plus this is simply a dot product. We would have taken that. But obviously we are talking about not one point but all the points on this surface. Just like we were talking here, we were talking about all the points in this whole volume. So we had this volume integral. Here we'll have obviously surface integral of the element. This will give us the value of distributed force, the work done by the distributed forces on any surface. Similarly, we can write this as this is displacement vector. Now using the same thinking, we can replace this by this is the contribution of the pressure or the distributed surface forces on in creating this work potential. Now last of all, this we need not spend too much time on this one. This is simply the work done by concentrated loads. The work done by a concentrated load is simply the nodal displacement. Here there is no summation. We are already in the nodal displacement domain. So the nodal displacements, any node which is subjected to a load P, it will have some displacement, and that displacement multiplied by that load component, the relevant node component, you'll get the work done. So there is no integration here involved here because we are just talking about one point. So when we have these expressions, I think it's safe to say that we are in a position to now use this potential energy expression and see where it leads us. So just putting in the values. So now this this potential energy becomes simply a matter of using this expression here and these expressions here. So if we do that, we should get I'm also opening the expressions as I write this. So I'm doing two steps in one go, but you can verify that there is no mistake here. This is the strain energy, and for work potential we have to use negative sign because the potential decreases and the strain energy increases, so there's a balance there. And if I put those values, first the body force, volume integral, then surface integral, these body forces, these are the distributed surface forces or pressure forces. And finally, no integration here. These are already reduced to nodal values. These we have to, in FEM we reduce all the forces, because if there are body forces here, actually what happens, you'll realize at the end, if there's a body force, although it acts on all these points inside the body, infinite points, but in FEM we have to take the cumulative effect and then apply it on nodes only, because in FEM you can only apply the loads on the nodes. Similarly for surface, though the forces are applied on the whole surface, but you take some sort of a summation and then apply it to the node. So we convert everything to nodal values, but concentrated load, it's already in nodal values. So because it already applies on just one point, and you make sure in your modeling that at any point that there is a concentrated load, you place a node there. So that's not a problem. Now we have got this one. Now you have to realize that this is just for one element, this one finite element within, and this E symbolizes that element, one element. So this whole expression is just for one element. Now this body is more than one element. There will be element here, element here. The whole body will be consisting of many elements. So if we talk about the whole body, consisting of E elements, total number of elements, let's call it E, then I think we can write this expression as the same expression, but we can write it as summation from one element to the total number of whatever the element is, 1000, 10,000, 20,000, whatever the total number is, and we essentially get the same thing. Inside these are the expressions for, these are summations for one element. This summation is for assembly of all elements, and we know how to do it with connectivity table. So we get 1/2. Similarly, we keep on using the same expressions, but this time the difference being we are taking the whole summation over the complete body, not just one element. So these values are within one element, but these integrals, they are about one element. But this summation, so what we do is, for one element we do all this sort of thing, and then we have to repeat that thing for the whole body, considering the all the other elements also, and that will give us the complete solution for the whole complete body. Now this is the expression for the, this holds over the whole, the summation. So this is achieved by assembly. Recall the connectivity table. And this inside these quantities, these are these summations, these summations within one element. You have to keep this distinction in mind. So what was the next step? Again, we start from where we started. This is the expression for the total potential energy. The principle of minimum potential energy says that this energy will be minimized at equilibrium, and that's what we are dealing with in static problems. So the expression for that is, you differentiate this with respect to the displacements of the whole system, whatever the total degree of freedoms are. You have to differentiate this whole thing by that number of degrees of freedom, and then you have to put it equal to 0. And obviously that is what we are going to do now, because this is the total expression for potential energy. This is not the minimized form of potential energy. You get the minimized form when you differentiate something and then put it equal to 0. So if we differentiate this and put it equal to 0, then what happens? I think it's easy to see here. You are familiar that this ut and this u, this basically means u square, and we have verified this in one of our previous lectures. They're just like an expression, an algebraic expression. For example, 2x square, and you differentiate it with respect to x, then it becomes 4x. So similarly here, u's, u transpose and u, they are written here because this is the only way you can multiply them, but essentially they are square of u. So when you differentiate this thing, this power, which is 2, it becomes 1, and this 2 comes down and it gets cancelled with this. So what we get as a result of the differentiation, I think it's easy to see, is we are going to differentiate this thing. So I think it's easy to see that when you differentiate it, it comes out to be, this 2 gets cancelled, b t d b, sorry, dv and u. And this u will become u system. Why? Because we are talking, because we would have assembled this whole thing. This whole thing would have been assembled, and because we are talking about from element 1 to e, then this u will not be here. We are talking about elements, so this was just an elemental u matrix. Here it will be the matrix of u of the whole system. We're talking about the whole system here. So this is one thing. Then similarly you will get, let's see this. Here again you have, here you don't have a square of u, it's just u. So what we get here is b d epsilon naught dv. This is the only thing we get, because this vanishes, goes away. Now move on to the next. Do we get anything here? We differentiate with respect to u. There's no u here, so this doesn't matter. This just goes away. What about this one? This one is here is just one u, so you'll have this vanishes, and you have this. And if you notice, the sign here is not negative, positive, but negative. Similarly, here you will get, this will go away. And again the summation, because the summation applies to all. And finally, what about this? The summation also applies to this. So this was nodal value. So now, because you apply the summation from 1 to the last element, so this simply, because there's no obviously this sort of integration involved, but this thing becomes simply P system, because you differentiate it with respect to u, and this vanishes, but this one remains, and this P, which was nodal values of the element only, now it will generate the nodal values of the whole system, and this whole thing becomes equal to 0. So I've just opened this summation to all, I've applied the summation to all separately, and then differentiate everything with respect to u. So where there was 2 is power of 2, it becomes 1. Where there was just 1 power, it just vanished, like all these. And here there was no u to start with, so this, it just disappears. So this is your equation. If we write this in a different way, the same way, but maybe more precisely, then it will become like this. Same expression, just I'll rearrange the values. Here I missed it. This is volume. You have to be very careful which integration is volumetric integration and which is the surface integration. And these, all these things we can take to the right hand side. change their signs, because this is 0, take it to because this is K matrix now, and all the other matrices are F matrices. So we can write, and we can again, the summation is the same for all these three. We can combine the summation and we can write it like this, plus all these signs will become positive. Again positive. The summation applies to the first three. Fourth one is already, like we said, it has already been, there's no summation involved here. This is just outside. Now, I think it's a very familiar expression for you. Ku is equal to F. This K, this is U, and this is F, where K matrix is nothing but this. So for any system, let's say 1D, 2D, 3D, subjected to whatever kind of loading, K matrix is simply, you get this expression for one element, integrate it, you get the expression for one element. But then that is just for one element. For the whole system, you have to integrate it over the whole, you get the summation over the whole body, and that is done by the connectivity table, what we call assembly. Now, F is a function of combination of initial force vector or thermal force vector. Now I'll talk about this thermal force later on. Body force, pressure force, but the first three are summed up by assembly, and finally the last concentrated force, that is added at the end. These three where F naught is equal to FB is equal to and FP is equal to so what you do is, you from element 1 to E, for each element you make these matrices, these expressions, you put in the values, you get the expressions for or the values for these for each element, but then you have to combine them using the same connectivity table. As far as the last one, the concentrated load is concerned, you just add the loads to the relevant nodes wherever they occur, and where they don't occur it's just 0. Now a word about this thermal force vector. Now there's no, technically speaking, there's no such thing as thermal force vector, but in FEM what this achieves is, because people have always have some confusion here, that first of all they say that if thermal effects don't directly influence the stresses, then why do we use them? I'll just give you a simple example and then we'll move on. Let's say this sort of a system is there. subjected to delta t only. No force, no applied force. Now, obviously, stresses are not involved here because this is just reasons length and that's all. But strains are here. If strains are here, then obviously displacements must be there. And if displacements must be there, then on the right hand side of this force vector, there must be some value. Otherwise, there will be no displacements here. If body force is zero, pressure force is zero, concentrated forces are zero, and there is nothing to allow the effect of this delta t to be applied here, then obviously the right hand side will be zero, which means the u's will be zero. But in this case, obviously we know that there is delta t while there are no stresses, but there are strains. So for strains to occur, obviously some sort of a force vector has to be there, and strains occur. But when we go on to calculate the stresses, then remember the initial part of the lecture we discussed that we have to subtract this. When there'll be strains here, but the strains will be completely the thermal strains. So before calculating the stresses, when we subtract the initial strains from the thermal strain, the total strains, we'll see that because the whole of the strain is a thermal strain, we'll know that the mechanical strain is zero, and so the stress will be zero. So this plays a very important part in any problem that has temperature changes in it. So now we are able to deal with all sorts of forces, body forces, pressure forces, temperature changes, to all sorts of problems, because this is an expression for 3D systems. For 1D and 2D and 3D, how we change them, that will be the topic of the next lecture. But these expressions, these are general expressions for all sorts of bodies in stress analysis for static problem. Now, if any element has m degrees of freedom, if then the element equations, k equations, will be k m into m, and the f vectors, all f vectors, will be m into 1. And if the whole body, the complete body, has n degrees of freedom, now this is, I'm talking about element, one element, then the system K will be of size n into n, and the system F will be of size n into 1. We'll verify these things in the next lecture too. Thank you very much.